Hello guys, welcome to BYJU'S Exam Prep, the most comprehensive preparation app for all the competitive exams. So myself, Murali Krishna Bokasamudram, I will be taking computer organization and architecture for this monsoon series. Please join quickly and mark your presence. I hope I am audible and visible to all of you. Am I audible? Please confirm me once. Yes. Okay. So today's session is about a set associative catch mapping. So previously we discussed about direct mapping in the yesterday's class, and those who have not attended yesterday's class, you can go through that, and this is an independent topic and you can understand very easily, and we are solving some problems on the set associative catch mapping. Okay, so please quickly join, and simply you can just say hi or hello and let me know whether my audio, video, everything is clear. Am I audible and visible to all of you? Okay, once again I welcome you all to my session, and please share the class information with your friends, and do subscribe the channel if you have not yet done the subscription, and also forward this class link with your friends, and please join in my Telegram group link. I'll just forward the link, and so in the comment box you can check after the class is finished. Okay, so let us start the session. Before that, please let me know whether my audio, video, everything is clear. Am I audible? Hello everybody, am I audible? Okay, so that's great, and we are going to discuss set associate mapping today. And once again I welcome you all to my session, and this is about my brief profile. You can just have a look, and I'm having 21 plus years of teaching experience, and I'm topper of NPTEL course in theory of computation, and also certified as international engineering educator through IZIP certification program, and I have mentored more than 50,000 students across the country in different core areas of computer science and engineering. Those are theory of computation, operating systems, computer organization, computer networks, digital logic, and ICT, information and communication technology. Hi Tushar Sisodia, good evening. So am I clearly audible? Please confirm me once and share the class information with your friends. So this is a very important class, and you are going to get minimum 2 marks in the GATE exam if you are thorough in this today's topic. That is set associative mapping. So definitely one question will come for 2 marks in the GATE exam. Not only in GATE, any other competitive exam like ISRO, NILIT, okay, and BARC, whatever it is, DRDO. So this is very useful. So all of you please share the class information with your friends, and please involve in problem solving. And let us start the session. Before that, you can just have a look at one slide. Actually, this BYJU'S exam prep is conducting a national level scholarship test, and for getting benefit of 90% off on the course fees. It's for GATE exam, GATE oriented paper will be there, and 30th July, that means on coming Sunday from 9 AM to 9 PM different sessions will be conducted. You can register right now, and you can take a step towards the success in the GATE exam by registering for it and attending the exam and getting a maximum benefit. Okay, hope I am audible and visible to all of you. So shall I start the session? Okay, shall I go ahead? And please do like the session if you are really liking it, and also share with your friends, and do subscribe the channel for getting more notifications, as we are providing a lot of free content for you, like not only the technical sessions. Apart from the technical sessions, we are also conducting the general sessions, okay, generic sessions, post-gate guidance, and motivational sessions, important topics, all those things. Okay, so in all for all round development of a student for success in the GATE exam, we are giving a lot of inputs. Okay, please try to subscribe the channel, and also inform your friends to subscribe who are preparing for the GATE and engineering services. Okay, now shall I continue? Hello Sudarshan, good evening. Hi Rajesh Arya, good evening. Yeah. Thank you so much, Tushar. And there is a workshop, a live and interactive workshop that will be on 1st August by Abhinav Negi sir. And for getting the master plan to conquer the GATE 2024 in 6 months, please attend this free live interactive workshop. Okay. So I hope everybody will try to make use of this facility and register for it. Now let us start the session. The first question, I think each one of you can answer very easily. If the associativity of a processor catch is doubled, Associativity doubled means what? For example, if the catch memory is a two-way set associative, then we are making it as a four-way set associative. And if it is a four-way set associative, we are making it as a eight-way set associative. That means n-way set associative, we are making it as a 2n-way set associative. Okay, so that is the criteria. So if the associativity of a processor catch is doubled while keeping the capacity and block size unchanged, that means size of the catch memory remains same and size of the block also remains same. Which one of the following is guaranteed to be not affected? Guaranteed to be not affected means which will not change. There is no effect on that. On which content it is guaranteed not affected means it will not be changed. Okay, I hope everybody have understood. So can you answer this question? Can you answer this question? Anybody? Okay, now I will explain. Usually in a set associate mapping, as you know, we are going to divide the physical memory. The physical memory address, which is given in bits, will be divided into three parts. So the first one is the tag bits. Okay, that is followed by set associate mapping, the set offset, and followed by byte offset. So these are the three things. So tag is to match with the tag present in the controller memory, whether to save it is hit or not, whether the required block is available or not, tag matching is required. Okay, and the set is which set it is. Okay, and byte is which byte within the block. So usually there is a formula here, number of sets. If you wanted to find out, number of sets is equal to number of blocks divided by n for a n-way set associativity. Number of sets is equal to number of blocks divided by n for a n-way set associativity. And the number of blocks is equal to catch size divided by block size. Okay, and what is guaranteed to be not affected? So option A, width of the tag comparator. So definitely when the set size is increased, so it will accommodate more number of blocks, so number of sets will be reduced. So accordingly tag size will be definitely having effect. Okay, tag size might increase when you are doubling it. Okay, and width of the set index decoder. So the set offset will be reduced so that the decoder required for decoding the information of which set also will be reduced. So there is an effect on the set also. And width of the way selection multiplexer. Way selection multiplexer is to select one set among the multiple sets. So when the number of sets are changed, obviously there is a effect on the multiplexer size we are choosing. This also will be having an effect. And the thing which is not getting affected is width of the processor to main memory data bus. It is immaterial how many sets are there, how many blocks are there, doesn't matter. It will carry the data according to the size of the data bus from processor to main memory. So there won't be any effect on the data bus from processor to main memory. So even if the processor's associativity has been doubled. I hope everybody understood this. Am I correct? And please let me know if you have any doubt. Yes, Tushar. And from next question onwards, I request everybody please try to respond to the question and please try to answer this. And the second question, a computer has 256 kilobytes, four-way set associative write back data cache and entry block size of 32 bytes. The processor sends 32-bit addresses to the cache controller. So the size of the address is 32 bits. And each cache tag directory entry contains, in addition to address tag, these are two valid bits, one modified bit and one replacement bit. This is in addition to the tag. Okay. So number of bits required in the tag field of an address is dash. So very simple, I am doing here. So what is the size of the physical address here? Size of the physical address is a 32 bits. So these 32 bits address we are going to divide into three parts as I told you in the previous problem. That is tag, and next one is set offset, and the last one is byte offset. This byte offset depends on the size of the block. So what is the block size? 32 bytes. Yes, so when you have a block size of 32 bytes, so each byte to identify we require 5 bits, because 2 power 5 bytes, 1 byte to identify we require 5 bits. So byte offset we need 5 bits. Byte offset we need 5 bits. To know the set of set, we require to the number of sets. Okay, let us say 256 kilobytes is the size of the cache and block size is 32 bytes and 4-way set associative. I am writing here. Size, so number of blocks is equal to how much? Number of blocks, what is the formula? Cache size divided by block size. What is the cache size? 256 kilobytes is the cache size. And what is the block size? 32 bytes. So number of blocks in the cache. This is number of blocks in the cache we are identifying. Number of blocks in the cache is equal to cache size divided by block size. What is the cache size? 256 KB is nothing but 2 power 18 divided by 2 power 5. So this is nothing but 2 power 13. So 2 power 13 blocks. To identify one block we require 13 bits if it is a block offset, but it is a set offset. We have to find out number of sets. Okay, number of sets is equal to number of blocks divided by n for a n-way set associative. Number of blocks divided by n, it is for n-way set associative. What is the number of blocks? 2 power 13. And what is associativity? It is given as 4-way set associative. The cache memory is a 4-way set associative. Okay, that means divided by 4. And that is nothing but 2 power 13 divided by 2 power 2. So it is a 2 power 11. So there are 2 power 11 sets. So to identify one set out of 2 power 11 sets, we require 11 bits. We require 11 bits. Now 11 plus 5 16, right? So 32 minus 16, remaining 16 bits we can use for tag. Remaining 16 bits we can use for tag. So option C is the right option. And the next question is about this problem only. It's like a common data question. And already we have solved this. The tag number of bits are 16. As you know, in the direct mapping yesterday we discussed, if you wanted to know the amount of extra memory required for storing the tag information, metadata. Tag information 16 bits plus 2 valid bits, 1 modified bit, 1 replacement bit you have to maintain for every block. Okay. So next question is about that only. I think now you can answer. It is not 14. It is Tushar. It is 16. You can see. A computer has 256 kilobytes, 4-way set associative. Same problem. Problem content is same, but the question is the second question. The size of the cache tag directory. That means cache tag directory means we maintain some additional memory in the controller for storing this metadata. Metadata means data about data. That means tag information and also the additional information because it is a write back cache. Like 2 valid bits, 1 modified bit, 1 replacement bit. Hope you understood. And please let me know if you have any doubt. Is it clear? And now cache tag directory is actually number of blocks into each block, how much information we maintain. Already we have solved it. So 16 bits of tag for every block we maintain like this. For every block, not for every set. It is for every block tag information we have to maintain. For every block, we have to maintain 16 bits of tag plus 2 valid bits, okay, and 1 modified bit plus 1 replacement bit. Total 20 bits. 20 bits of information we maintain for every block. Like that, how many blocks are there? Number of blocks we know. Number of blocks is cache size, that is a 256 KB divided by block size 32 bytes. Already we have solved it. So this is a 2 power 18. 1K is 2 power 10. 256 is 2 power 8. So 2 power 18 divided by 2 power 5. That is nothing but 2 power 13 blocks. So these 2 power 13 blocks, we have to maintain this tag information of the metadata. That is a 20 bits. So total 20 bits you have to maintain for every block. So 2 power 13 into 20 can be written like this. 2 power 10 into 2 power 3 into 20 bits. In the form of bits if you write, it is something like 2 power 3 is 8. 8 into 20, 160. 2 power 10 is 1K. So it is, it can be written as 160 kilobits. It can be written as 160 kilobits. So option A is the right option. Hope everybody understood. If you have any doubt or concern, please let me know. Yeah, 160 kilobits. If you wanted to convert into bytes, divided by 8. So 20 kilobytes. Either 20 kilobytes or 160 kilobits, because 1 byte is 8 bits. Okay. Shall I go for the next? Exactly. Tushar. Hi Shyam, you are right. Shall I go for the next problem? Please let me know. If you have any concern, any doubt, please ask me. Don't hesitate to ask your doubts. I hope I am audible and visible to every one of you very clearly. Otherwise, please let me know. And the question number 4. It is also a very good question. It is in the form of some generalized symbolic notation. If you know the concept, you can answer. The size of the physical address space of a processor is 2 power p bytes. The word length is 2 power w bytes. And the capacity of the cache memory is 2 power n bytes. The size of each cache block is 2 power m words. For a KWA set associative cache memory, the length in number of bits of the tag field is, okay, size of the physical memory is 2 power p bytes, means every physical address is containing p bits. Every physical address is containing p bits. Okay, and the word length is 2 power w bytes. So word length is 2 power w bytes. And the capacity of the memory is 2 power n bytes. Cache capacity. 2 power n bytes is the cache capacity. And the size of each cache block is 2 power m words. So block size is 2 power m words. And one word size is given as 2 power w bytes. Okay, na? Word length. So block size in bytes is nothing but 2 power m words, where every word is of 2 power w bytes. So this is the block size in bytes. So 2 power m plus w bytes is the size of the block. 2 power m plus w bytes is the size of the block. Hope you understood. Now only thing we have to find out is tag bits, number of bits you have to find out. So symbolically we have to do it, and I am doing it here. So we are considering the total address here is of p bits, because physical memory is of p bits total. Out of these p bits, we are dividing into 3 parts. So tag, and then set offset, and then byte offset, because it is a byte addressable memory, because it is mentioned as 2 power p bytes. Hope everybody is following. And as I know, I have converted the size of the block which is given in words into bytes. So 2 power m plus w words are there, 2 power m plus w bytes are there in each block, means so byte offset is m plus w. So we require m plus w bits to identify one byte out of the 2 power m plus w bytes. Now first of all, number of blocks you have to find out to know the set offset. So number of blocks is equal to cache size divided by block size. Number of blocks in the cache is equal to cache size. What is the cache size given? 2 power n bytes. So there are 2 power n bytes, and divided by size of the block is a 2 power m plus w. So we can say it is a 2 power n minus m minus w. This is the number of blocks. So to identify one block, we require n minus m minus w bits. Okay, and number of sets also we have to find out. Number of sets is equal to how to identify number of sets? Number of blocks divided by associativity, KWA set associative. So it is a 2 power n minus m minus w divided by k for a KWA set associative. But if you wanted to have in 2 powers, and we can write this value as k value as log 2 power k base 2. So log k base 2. So it is something like this. So we can write this as a 2 power n minus m minus w minus log k base 2. We can write like this. That means To identify one set out of the sets available, of these many sets available, we require these many bits, n minus, m minus, w minus, log k base 2. And remaining bits, whatever are present out of these two are addition, and we have to subtract from p. So tag bits is equal to, I can write like this, tag bits is equal to p minus of set plus this one. So it is a n minus, m minus, w minus, log k base 2 plus m plus w. So here m cancel, w cancel. What is present? It is a p minus n, minus into minus plus, p minus n log k base 2. These are the number of bits required for tag. P minus n plus log k base 2. So like this we can find out. Okay. So p minus n plus log k base 2 is there in option B. Option B is a right option. Exactly. You are right, Tushar and Shyam. Okay, na? Shall I go for the next? Okay. Now I shall move on to the last question, question number 5. I hope everybody is able to follow this. A cache memory has 128 blocks. It is a numerical answer question and organizes 4-way set associativity, and main memory contains 16,384 blocks, and each block contains 256 8-bit words, means 256 bytes each block. So block size is indirectly given as 256 bytes. So block size is equal to 256 8-bit words, that is nothing but 256 bytes. That is the block size. And main memory contains 16,384 blocks. How many bits are required for physical address and how many for tag comparator? That is what we are supposed to find out. So here what we have to find out, number of blocks also given. Number of sets is not given. So main memory size, physical address size is not given. That depends on main memory size. So main memory size we can take here. So main memory size is equal to 16,000. Main memory size is equal to 16,384 blocks into each block is 256 bytes. And we can write this as 16,384 means 2 power 14 into 2 power 8. So it is a 2 power 22 bytes. Out of 2 power 22 bytes, to identify 1 byte, we require 22 bits. So physical address is 22 bits. Physical address is 22 bits. Okay, na? And what about others? Tell me. The thing is, we have to find out tag bits. So to identify a tag bit, we have to divide the physical address of 22 bits into 3 parts. What are those 3 parts? I hope everybody is following. Tag bits, and then set offset, and then byte offset. Byte offset purely depending upon the block size. Block size is mentioned as 256 bytes. So it is 2 power 8 now. So 8 bits are used for 1 byte out of 2 power 8 bytes. And number of sets, as it is a 4-way set associative, number of sets is equal to number of sets is equal to number of blocks in the cache 128 divided by set size 4. So it is a 2 power 5. 2 power 7 divided by 2 power 2, 2 power 5. So 5 bits are used to identify one set. So 8 plus 5, 13. 9 bits are used for the tag. 22 minus 13, 9 bits. So the set offset, the tag bit should be 9. So the right answer is here 22, 9 bits. 22 bits are physical address bits and 9 bits are for this one, tag bits. Okay. That's all for today. I hope everybody have enjoyed the session. Please do subscribe it and please press the bell button for getting notifications. And also please do share with your friends. Exactly, Akhil Gaud, you are correct, 9 bits. And tomorrow also we are having a session. Please attend at the same time. And I will cover interrupts and direct memory access in tomorrow's session. Okay, the problems related to interrupts and direct memory access. And don't skip the classes. And if you have not covered any of the class earlier, those are available. All the links are shared in the Telegram group. Please go through that. Direct mapping also we discussed. That's all for today. Thank you so much. Good night. See you all. Bye bye.